I now start module 7 or chapter 7, which is the Kalman filter. So we're going to quickly get into actually deriving the Kalman filter, describing how it works, etc. But because the Kalman filter itself and how to derive it is going to involve a lot of matrix, sort of complicated arithmetic and calculus, minimizing a trace, etc. That's how I'm going to do it. So I want to go through a simple example where we can just use good old algebra, scalar algebra, and scalar calculus to show you the process here, which is going to be this blue, best linear unbiased estimate, because that's the basic method we're going to use to do the Kalman filter. And actually, we're also going to introduce this concept of doing it recursively. So let me go through this simple example to show you kind of where we're headed. We have this true state x, which is just a scalar. It's not a vector. We have the first measurement, z sub 1, and a second measurement, z sub 2, where the errors on those measurements, we know the first and second order statistics. They are zero mean. We know their variances, and they are uncorrelated with each other. So that's the problem statement. Now we want to go through the blue process. Linearity means our estimate is some kind of linear function of the measurements. So it's going to look like this. The error is defined as the difference between our estimate and the actual state. Unbiasedness means this expectation is zero. The expected error is zero, or the expected value of our estimate is the expected value of the state x. So what is that expected value of our estimate? Well, here's our estimate. We put that in there. And then we substitute in what these z's are. We get that. But take the expectation term by term, and you get this relationship between the C1 and the C2, and also the D equals 0. Because, well, this simplifies to that, and that must equal this expected value. So we just algebraically solve a little bit of it. We've got, of these three initial unknown parameters, we're down to just one, C sub 1. So here's our estimator right now. It only involves C sub 1 and the two measurements. Now we impose best, to the minimum mean square error. And how do we go about doing that? Well, we plug in what the x hat is, you get that. And then we plug in what the z's were, you get that. Multiply it all out and do some algebra on the way. I'm not going to go through this in detail, but here we get what this is, what the mean square error is. So now we can just, by scalar calculus, find the C sub 1 that minimizes this guy. So take the derivative of that with respect to our parameter C sub 1. Get that simplified a little bit, and now you can solve for C1. And once you solve for C1, we get C2. We're related to each other. And you can check on the second order condition. It is strictly positive, so we indeed found a minimum. So here's the solution to the problem. It's this weighted sum of the two measurements, and here's how you weight them, using the variances and variances of the measurements. And we also know how accurate our estimate is. What's the expected value or the variance of the in the error of our estimate? And we know that. So we just found the best linear unbiased estimate given those two zero mean measurements with no. And we also know the variance of the error of our estimate. What if we looked at that problem recursive? I think I'll do that in the next video because it's going on pretty long.